Hello, everyone. Today we'll be looking at Ramsey's theorem and its infinite version. So I'll start off just by saying, in case no one knows, that for a set x, we denote by x squared with the square brackets to be the set of all subsets of x which have two elements. So up here, you'll see we have this notation, so n squared. So this is all like pairs I and j, such that I and j are natural numbers. So these are the same definitions here. It might be a little more clear based on how you know points are in n. Okay, so the statement says that if you take all of the natural numbers and you connect all of them with each other. Everyone is connected to everyone else. We consider this set. We assign a color to every single point in here. We can think of this set as like the edges between our numbers, right? If we assign a color, either red or blue, to every single edge, I'm going to refer to the members of this set as edges, but if we assign a color to every one of these edges, then there will be an infinite subset, A of n, such that any edge between 2 points in this set A will have one color. So there will be a color, it's either going to be red or blue. Every edge between 2 points in A is either red, or every edge between every 2 points in A is blue. So this is known as Ramsey's theorem, and we're going to prove it now. Okay, so proof. So we will set A0 to be this entire set, and we will fix a point x0 in A0. So by the universe we're in right now, we know that x0 has infinitely, I'll say x0 is incident to infinitely many edges in n. And this is true because we have the edge x0, 1, x0, 2, all the way up to x0, x0 minus 1, x0, x0 plus 1, and this goes on forever because there are infinitely many natural numbers. So we have infinitely many neighbors. And each of these edges between its neighbors is either going to be colored red or blue. Because we have infinitely many, this means by pigeonhole argument that it must have infinitely many red edges or infinitely many blue edges. Because if not, then it had only finitely many red edges and finitely many blue edges, which contradicts the fact that it has infinitely many edges. So we'll say, then there exists a color C0 in the set of red or blue, such that x0 is incident to infinitely many edges with color C0. If there does not exist such a C0, then x0 has finitely many neighbors, since we color every edge. Because if we would take all of its blue neighbors and all of its red neighbors, and there would be only finitely many, but what about all of the remaining edges from x0 to another point? So there are infinitely many edges incident to x0 with color C0. So because of this, we can define the set A1 as follows. So we'll define the set A1 to be the set of x in A0, such that the edge between x0 and x has color C0. So note that this set is also infinite by the above, because we're now just taking all of the neighbors of x0 such that the edge, it has color C0. Okay. So now this set is infinite, so we can do something similar. We will fix then x1 in A1. And by the same argument, A1 is infinite, so x1 has infinitely many neighbors in A1. Neighbors in A1. And between x1 and all of its neighbors is an edge with a color, either red or blue. So by the exact same reasoning as above, there is a color C1 in the set of red or blue with x1 incident to infinitely many edges with color C1. Infinitely many edges between x1 and a point in A1. Okay, so this is true. Remember, A1 is infinite. X1 has infinitely many neighbors in A1. Between x1 and all of these neighbors is an edge which is either colored red or blue. There are only finitely many colors. There are infinitely many such edges. So there is a color C1, either red or blue, which will be such that x1 is incident to infinitely many edges with this color. Okay, so because of this, we can go ahead and define another set, A2. And it will be all the points x in A1 now. So before we were working with A0, now we're going to work with A1, x in A1, such that the edge from x1 to x has color C1. So this looks really similar to the above, so it's kind of hinting at where we're going. I'll just point out here that A2 is infinite. So this set is infinite by construction. And I will note that x1, like for every x in A2, we have that the edge x1 and x has color C1. This is important for our induction. So now we're going to define infinitely many of these sets. So we're going to fix an integer k bigger than or equal to 3. And we will assume we have a1 all the way up to ak minus 1. And we have x1 all the way up to xk minus 1, such that xk is an ak, or I should say xi and ak for all I less than k. And then also we have colors C1 all the way up to CK minus 1. And we know by induction that AK minus 1 is infinite. AK minus 1 is infinite, and that XK minus 1 is in AK minus 1. So by the same argument as above, we can find infinitely many points in AK minus 1 such that edges between those points and xk minus 1 are one color. So by induction then, the set AK will be infinite, and we'll define it as follows. All the points in here, that's what I just said essentially, such that edges between xk minus 1 and x have color ck minus 1. So we have a point xk minus 1 in ak minus 1. ak minus 1 is infinite. We will find a color ck minus 1 such that xk minus 1 has infinitely many neighbors in ak minus 1. with this color, so that with edges between them of this color. So by induction, we're done. We can define infinitely many of these sets. And we have the property, so we have A1, A2 forever, we have X1, X2 forever, and we have color C1, C2 forever. And then with the properties by induction, as we proved, such that for any k and n, we know that, first of all, xk is defined in ak. ak is infinite. We have ak plus 1 is a subset of ak. And by induction, as we see from above, for every x in, or I'm going to say, yes, I'm just going to say for every x in ak plus 1, we have that the edge xk to x has color ck. So because I've said here k and n, I don't want to use this because what if k equals 1? I'm going to subtract 1 and it's going to be a0. Oh, no, that would actually work. That was a small mistake. This is fine. This is just taking the set following ak in the induction. So I could have also said here, I'll just write it, for every x in ak, the edge xk minus 1 x has color ck minus 1. But you'll see later why I'd rather write it as I did above. Okay, so with this, we're ready to define our monochrome set A. Now we will define A as follows. We have a sequence, C1, C2, forever, right? And each of these is either red or blue, right? So red or blue. So by this pigeonhole argument again, there is a color C, red, blue, such that C equals CK for infinitely many such K. If not, there are only finitely many terms that are red in the sequence and only finitely many terms that are blue in the sequence. But the sequence goes on forever, so that can't happen. So there is such a color C. And then with this in mind, we will define A to be the set of all xk's as we've constructed them, such that their associated color ck is C. And this will do it. And to see why, so take xi, xj in this set of two element subsets of A. And we'll assume that I is less than j, as is customary. So from this property, inductively, we know that aj is a subset of aj minus 1, right? Because ak plus 1 is a subset of ak. This is a subset of aj minus 2. And this will continue all the way up to ai plus 1. So this implies, so xj is in aj implies that xj is in ai plus 1. Now, as we've written up here, for every x in ak plus 1 or ai plus 1, the edge between x and ak has color ck. So in this case, the edge between xi and xj has color ci, right? Just like we could just replace I here with K, and we'll see exactly that we have a point. We have a point in X in AI plus 1. And this means that this point and Xi, the edge between them, has color Ci. And that's exactly what we see up here. So let me just erase these changes. But Ci, Xi was in this set up here. So Ci is C. Therefore, all edges in A2 have color C. And by the argument above, because of this set is infinite. So that concludes the proof of the infinite Ramsey theorem. Thank you very much, and please let me know if you have any questions.